Robert Griffin from IH1NC. So, floor is yours.
Can you hear me? Okay. So I'm Robert Griffin, and I get the pleasure of following them. So I'm going to be talking more on how we can get our robots to walk without really bent knees, in our case using the older, slower, fatter version of their robot. So as Chris and Manoj kind of pointed out on the very first talk, we've done a lot of walking with our robot, and in pretty much every one of these videos you see them walking with really, really bent knees. This is somewhat a modeling choice. So we typically use this concept of a linear inverted pendulum. It's really often that we model walking, as I'm sure you all know, many of you better than I do, that it resembles an inverted pendulum. But with this linear, when we linearize it, it becomes much easier to control. You get uncoupled dynamics. But to do that, you basically assume that it moves in a flat line, and then you can kind of relax this assumption a little bit, and you can come up with height plans to go over rough terrain. However, I decided to collaborate with one of the presentations that we showed earlier. And if we do this with a person, now note that we did take safety into account here. It looks kind of ridiculous. This isn't at all how people walk. So the idea then is, well, how can we get these robots to resemble more closely the motions that you get out of a human? So we made some good progress with that. This is just kind of a quick demo using our robots. So in this case, it's using what I'm going to kind of go into to walk with these straighter legs. Didn't get it going very fast, and I was going to try and get some better videos, but then the robot broke, and we don't have an awesome repair team here to fix it for us. So typically, to do these balance, am I not showing up? Okay, so we typically regulate our contact forces using some momentum rate of change. We're trying to control a center of mass position. You do that, you specify a momentum rate, and then you can compute some reaction forces. So one way that you could do this is you could look at it and say, okay, well, where does our center of mass position need to be to have straight legs? Instead of doing that, we could look at it and say, well, instead of trying to figure out a center of mass position to have straight legs, let's just control the legs directly and try and drive them to be straight. So we can introduce these virtual actuators on the legs and then use this horizontal momentum control. The reason we'll keep using the horizontal momentum control is if you start trying to shift the weight around, just controlling the forces with these leg actuators, I can't make it stay on the left, I can't make it stay on the right, because it would kind of go back to this equilibrium in the middle. So to do that, we only want to get a certain portion of this reaction force. So we can kind of look at our whole body controller in this situation. So this is some equations. Basically the goal is to have an input set of tasks and then optimize to compute an output set of joint accelerations and and reaction forces. So one of the approaches that people have done before to kind of do like singularity escape, so when the leg goes straight, how do you get out of that, is you actually project this task into the null space of our big Jacobian J for everything. So to do that, we can define a leg actuator, we can compute some knee accelerations, ankle accelerations, and hip accelerations. We can actually add that as an objective in this bottom equation to our cost function. So basically, every time I move my laptop, we get a nice little flicker, so I guess I'll stop touching it. So if we leave this height uncontrolled, what typically happens if you're just using it for a singularity escape, you only start to open up this null space as your leg goes straight. But if we leave the height completely uncontrolled, there's always a non-empty null space for this task. And this works pretty well, especially in sim, where everything seems to work magically. This is kind of the results using this approach, where we just are not specifying a height trajectory at all and the legs stay straight. One of the things, though, that's critical to this motion is toe-off. And I know there's a lot of people that know a lot more about toe-off, especially when it comes to how humans employ it. But just from a purely kinematic perspective, this is really important. If we don't allow the robot to toe off, so in this first video, it's walking with completely flat feet, to shift its weight over to the front, it has to bend that front leg a lot. And you'll really see that right there. However, if you add the toe-off motion, that's less necessary. So to control this toe-off action, we actually just move all our contact points into the foot, or into a toe point on the foot, and then we leave this pitch motion of the foot completely unconstrained. So that's actually kind of there's some questions on some of these robots, like how do you control that toe-off action? Do you tell it a feed-forward torque, feed-forward velocity? In this case, we don't tell it anything. We just let the optimization figure it out instantaneously. We say we have a desired reaction force. How do you best use your ankle to achieve that reaction force? So using this approach, you kind of see some good results, but when you go to doing step downs, if you're just telling your legs to be straight, you're controlling the leg length here, it won't actually start to drop that foot until you override, until the cost of keeping the leg straight is less than the cost of tracking the foot. So that's bad. So to kind of compensate for that, we can actually introduce the state machine for the leg length, where we say, first your foot touches down, you want to straighten, and you keep it straight, and then near the end you start to collapse. And then you just bend to escape the singularity, and then you extend it all the way. And that actually kind of helps enable that. And when you kind of add all these things together, you can start playing with it and see what you can get your robot to do. Again, most of this is in sim. So I figured, let's see how long of a step we can take. So this is just having it, I'll move the, so this is a 1.5 meter long step. Given this probably isn't physically realizable on the robot, I don't think it can move it. It doesn't have the range of motion to do that. Probably doesn't have the actuator authority to do it either. And I decided, it'd also be cool to check out what happens if I have it pause in the middle here, so it stops, and then this is one of the advantages of leaving this task in the null space, I think, kind of as a hierarchical thing, is it will just automatically bend that front leg to start, to be able to move the center of mass forward, because that's our main objective, and then within that, you can then bend the leg or keep it straight. And then we can kind of start tying this idea of collapsing the leg back into what Jerry talked about, which is probably going to draw some contention here. This idea of the leap of faith, where if you miss this talk, it's basically collapse your stance leg during swing to kind of fall onto your next step. So one of the cool things is big step downs required collapsing a little bit faster than what I noticed with just regular walking, which makes a little bit of sense. So here I decided, well, let's have it step down 40 centimeters. You'll notice the back foot gets a little squirrely. It automatically, when it goes to stand, transitions back to full support, and I really didn't want to hack that together to get a good sim. And so this is kind of cool, but I think the cooler part was if I stop telling the robot that it's about to step down 40 centimeters and instead say, hey, you're a 20 centimeter step. So it thinks that this step is half the depth that it actually is, and it really looks almost the same. So it's collapsing, or it's having to take a 40 centimeter step, but thinks it's only taking a 20, and it doesn't really affect the robot that much, in simulation at least. And then, continuing with playing with it, let's see what we can do. So just kind of seeing, well, as we walk it, we can push it and combine some kind of step adjustment stuff. So it works pretty well. We get a nice little, the robot pauses to kind of regain balance and stuff. That's another little feature. And then just kind of seeing if we were to kind of go over rough terrain, how does this look? So again, I'm not giving it a height trajectory. I'm just saying try and get your legs to be pretty straight. I think this looks pretty good, kind of from a high level. And then it also translates pretty well to hardware. So you'll notice some screen splices. That's because I didn't really want to make you all sit through the point where I'm telling the robot step on this next cinder block, because that's pretty boring. We didn't really want to test this with the footstep planer at the time. It wasn't quite ready. So my favorite part is the end where we actually get to the step down. Just a second. So I thought that looked way more naturally than having the robot kind of lower itself the way that we've typically done. And I'm hoping that, when you combine that with toe off, one of the things that in the DRC we had to be really careful with was when do you step down because of the kinematic limits of the toe. Well, if you just force toe off, that's not as big of an issue anymore. So I just want to thank everybody that helped me with this. Georg Wiedebach, Sylvain, my former advisor, Alex Leonessa, and Jerry Pratt and the rest of IHMC. So this is all open source software. You can check it out on our GitHub page. And then if you want to learn more about it, Sylvain will be giving a tutorial on the whole body controller core. And with that, I'd like to thank you guys.
Question over there.
Hi. So, in addition to achieving those task performance, what other performance have you seen in terms of improvement, like efficiency or torque or others?
I never directly looked at the power consumption, but I would imagine, especially standing there, you're not having to keep your knees really bent anymore, so your torque on your knees goes considerably down. It's now kind of transmitting more through the actual structure of the robot, so I would believe there would be some efficiency improvements, although I haven't actually looked at any data to officially say that. So.
Okay.
In the back. So I think.
One of the nice things is, about the LAPM is that you can do long-term planning from its linearity. Do you see a way forward once you've broken that by allowing, the center mass height to go up and down within your framework?
So, not particularly. One of the things that I was mainly interested in this is kind of the instantaneous control problem. So we are still in all of the simulations and videos and stuff that I showed, we're still using this linear inverted pendulum model for the planning aspect of it. I do think that to kind of capture some of the better features that make it more human-like, you do have to start looking at that height variation. Particularly, one of the things that, just from an animator standpoint, you also seen other data on this, the human raising its center of mass before heel strikes, that push-off phase in the toe-off, or from toe-off, it's not really something that you can capture very well using this linear inverted pendulum model. So we do get a nice kind of sinusoid type center of mass height motion from this, but it's still not quite the same. So I don't know exactly what the way forward is. I think that we do need to start looking at some more advanced planning to get, if we wanted to get exactly like a human.
With the straighter legs, don't you have collisions now? And then doesn't that also mean that, so it differs from what you would expect from linear inverted pendulum as far as how far to step for a capture point?
So
when stepping, you have a collision, and so you should lose some energy, and then, so your capture point is a little bit different from linear inverted pendulum.
Yes. So if I understand correctly, basically the fact that you're introducing this kind of almost an impulse whenever your foot hits the ground. Yeah, we do have that. That's definitely a problem in it.
Well, I would expect it to be
kind of an advantage.
Advantage, yeah, because you don't have to step as far.
Yeah. So that's one of the things that we are starting to look into is how can we start to exploit ramping up that and use an impact. So. Kind of going on to what Jerry was saying, whenever you have this big step down, if you have that impulse to kind of negate your center mass velocity, how can you use that from a control perspective to come to a stop more quickly? The other advantage, or the other flip side of that is, how do you cancel that out if you want to continue walking smoothly? And that's something that we're trying to look into a little bit. I don't have any clear answers yet. It's kind of an open question.
So we're taking one last question.
It's on. All right. So a lot of people have been talking about toe off and have had some kind of interesting mechanical designs to aid themselves in that. Mm-hmm. Because you're talking about the importance of toe off, do you think it would be beneficial to actually have some kind of toe, whether it's I don't know, either like a joint or like some kind of difference in elasticity there, something like that, to kind of aid what you were talking about, where you're having this fall and you don't necessarily need to properly model those dynamics, having that compliance can just help you out with that?
So I do think that the idea of including a toe on the foot is very interesting. I don't have a good answer for how to then control it. Completely compliant toe, you then have this weird question of how much of the force can you actually put into the toe if it's a passively compliant mechanism. But I think we're a little more focused on general motions and general concepts, and how we aren't let's have a robot walk for 30 minutes. It's more let's have a robot perform a set of tasks, and how can we make those be a little bit more natural. If we were going to focus on really efficient walking, I would definitely say that that's an area worth exploring, though.
Okay, let's thank Robert.
Okay.